you can see that what we're learning is not too different. Um, this looks very familiar. It's just a little bit of the notation. Anybody catch what's different in the notation? Yeah, it's instead of small f, it's written as large F prime. And so really all that means to us is this. The integral of the, what is a word we use to describe, say, derivatives? Slope, rate of change. The integral of the rate of change is the net change. The integral of the rate of change is the net change. So let me give you an example here, okay? If I talk about distance, like the position of an object, the distance of an object at a certain position, okay, at a given time, if we take the derivative of that, what do we get? What do we call that? If we take the derivative of placement, the derivative of position, we get velocity. That sounds familiar, right? So if you take the antiderivative of a velocity function, that will give you the net change of the position of that function over a given time. So I think that the velocity is the best example we can use. So I'm going to do one problem that involves velocity, and I think that will kind of summarize your learnings. Not a lot that's new, but just conceptually a few ideas. So let's do example 1 here, okay? I'm just going to pull one directly from your book. It's a good example. Particle moves at a velocity of v of t is equal to t squared minus t minus 6, where t is in seconds. A, find the net change or the displacement. B, find the total distance traveled. And we'll limit our interval from 1 to 4 seconds. 1 to 4 seconds. So let's just gather our bearings about the problem initially. We have a particle that's simply moving. Okay? Let's just think about this for a second. You have a particle that's moving along a line somewhere. If I plug in my time, say time 0, at time 0, what's my velocity going to be? Negative 6. So it's moving in which direction? Yeah, it's moving left, okay, in the negative direction. If you plug in 1, 1 squared is 1 minus 1 is 0, minus 6 is negative 6. So at time 1, it's also moving still in the negative direction. So it's going to be moving in the negative and the positive direction. Now, let me just kind of show you the example, because this is something that should relate to our previous knowledge and our learning. If we start here and say we head in a negative direction and a positive and then negative again, okay? Now, no, we're going to make it really easy this time, okay? Okay? If you think about that, let's say that my initial position is 0 and my end position is -4, okay? Um, how far has the object moved from its original position? No. Let me just focus. It's just moved 4 units or -4 units from its original position. Now, what were you going to say, though, Brady? Because that brings me to my next point. Right. So its displacement would only be 4 units, but its total distance traveled would be this entire piece, right? So as opposed to doing all the work that we did before, now that we have the velocity function, all we need to do is take the antiderivative and evaluate the integral, and that will give us a net change, but there is a small subtlety here. Yes, question? At time negative, or no, that would be my position. So it would be -4 units removed from its original spot. I don't know. I'm just making it up. I'm just saying, let's suppose that that was the motion of the object and it ended up at -4, okay? So the first thing I want to do is I want to get a graph of this function. Let's do that, okay? So take out your calculators. And I'm just going to graph this function. And I'm going to go, let's see, y equals x squared minus x minus 6 and I'm just going from the interval from 1 to 4. So on my calculator, I'm just going to make my window x minimum. We'll say 0 would be fine. My x max, 5 would be fine. On my y minimum of -6, I'll make it say -10. My y maximum, I think, I don't know, we'll say somewhere around 30. We'll scale every 10. Maybe that should give me a general graph. So that's what I'm going to look at. Okay. Anybody else? It looks like my graph, I could go a little bit lower. I'm going to change my window just to get a better view here. I'm going to go, say, 20. Okay, that's a little bit better. So what we're doing is we are looking at the travel of the function from the time 1 to the time 4. And they say that that's equal to the integral. The net changes. So if I do second calculate, you guys can see what's happening here. If I do my integral simply from 1 to 4, what do you notice about that area? Some of it's negative. In fact, if you would take the negative and add it to the positive, what do you think the result would be? Do you think it would be more negative? So what that tells us is that the object, is it sitting on the left side or the right side? It's sitting towards the left. However, there's all this area is movement, right? All this area is movement. So what we can do is if we find the integral from 1 to 4, that will tell us its total displacement. We'll say it's going to be just to the left. But if we find the absolute value of each area piece, that will in fact give us the entire distance that the object has moved. So we're going to break it up into 2 pieces. Let's do the first one first. It will be nice and simple, okay? We'll do the first one, okay? So all I need to do is just say, well, in order to find the net change, part A, I'm going to evaluate the integral from 1 to 4 of x squared minus x minus 6 dx. Easy so far, right? Okay, so let's evaluate that. What's my antiderivative? A little easier than the other days in class, right? Like yesterday. I guess the antiderivatives you guys were finding yesterday were a little bit more difficult, right? So we'll enjoy these easier ones. So now we plug it in. 64 over 3 minus 4 squared is 16 over 2 is 8 minus 24 minus, now I'll plug in 1 1/3 minus 1/2 minus 6. I'm just curious because I know how I've always done this. What is your guys' first step from here? What do you guys like to do when you see this part? When you get this far in evaluating the integral? Okay, I I like to pair up the 64 thirds and the 1/3 right away. You don't? Oh, well, 64 minus 1/3 is 63 over 3, which is just 21. So that's you don't want to do that. Are you serious? Okay. All right. Well, so you got tell me how you want to do it. Ashley, tell me how you would do it. Or you just plug it all into your calculator. Oh, so you guys do this. You guys go, let me just make sure that I understand. You guys go 64 divided by 3 minus 8 minus 24, enter, second, whoop, math, convert to fraction. That's what you do? That's great. All right, good. All right, wonderful. Okay, be, because you guys do it like that, I trust that I trust you're all capable of using calculator. I'll just show you what I do really quick, and then you can decide what method you would like. I would go like this. I would go 64 over 3 minus my 1 over 3. I have a minus 8 and a minus 24, which is a minus 32, and then plus a 6, which is minus 26. And then I have a minus a negative 1/2, which would be a plus 1/2. Also, and this is just 63 over 3, which is 21 minus 26 plus 1/2. So negative 5 plus 1/2 is equal to negative 4 and 1/2. So that's how I do it. Okay. All right. All right. That's great. All right. We all get to make a choice in how we want to do it, right? So to answer question A, the displacement is negative 4 1/2 units. Okay. So you're right. It moved to the left. It moved to the left. Negative. Part B forces us to account for both the positive area and the negative area. Well, I have to find where it crosses over from positive to negative. So I'm going to do this, okay? Over the interval 1 to 4, I want to know where does t squared minus t minus 6 equal 0. I want to know where it crosses over that spot and goes from positive area to negative area. And so when I set this equal to 0, I can factor this. Was it factor 2? T minus 3, t plus 2. So that gives me solutions at 3 and negative 2. So at t equals 3 is when it changes from positive to negative. Right? So in order to find the whole area, I have to break up the positive portion and break up the negative portion. So I have my positive area. I have my negative area. The positive area will be from what? What will be my bounds of integration? If we look back at our calculator, we could see the bounds of integration are from 3 to 4 for the positive area with a little knowledge of the graph. And what would be the bounds for negative area then? 1 to 3. So we're going to find the positive area from 3 to 4 of, again, t squared minus t minus 6 dt. And we're going to, make sure that we find the absolute value of each, and that will give me the total distance that is traveled. And so this is going to be positive. We know that. So I will have t to the third minus t squared over 2 minus 6t. It's not that bad. We already know what it's evaluated at 4, right? I mean, it came up with what? 64 over 3. What did we have? Minus 8, minus 24. I mean, that was the first part. Now we just need the second part. Let's see. 3 to the third over 3 is 9. Minus 3 squared is 9 over 2. Minus 18. So you guys are all doing that on your calculator. You want to give me the result of that? So now, for the negative portion, again, I will do, t to the third over 3 minus t squared over 2 minus 6t evaluated over the interval from 1 to 3. And we already know what it is evaluated at 3. We have that written down. 9 minus 9 over 2 minus 18. Right? We already have that. We already have the 1, don't we? Evaluated at 1, we said it was 1 over 3 minus 1 over 2 minus 6. Did you guys get 59 thirds? What sure seems like it should be negative, right? Negative 31 thirds. We'll check with our calculator. Number 7, the lower limit of 1, upper limit of 3. Negative 7 and a third, so that would be negative 22 thirds. So what we really have here then is the total displacement, or the total distance that the object traveled, would be the absolute value of each, right? Summed together. So if I do that, I have 17 over 6 plus 44 over 6, which is 54 plus 7, 61 over 6, which is equal to 10, 1/6. Okay? And that's, yep, that's what your book has. Well, yeah, but the idea is that you have a broken integral. You have to break it up into two pieces. So I just have a couple problems I want you guys to try like that. That's it. You have the rest of the time to work. So I'll write your problems on the board. Please just look at page 358, numbers 53 and 54. Now, you guys, we've talked about more rates of change. We've talked about marginal cost function. We've talked about all sorts of pieces. So the applicability goes beyond this, but let's just introduce that first piece. Maybe tomorrow we could do a little bit more.